So it's a pleasure to introduce my colleague and good friend Amin V, who's here from both UC San Diego and from Google. So he's simultaneous, like the uncertainty principle or the wave-particle duality. It's not entirely clear where he's from right now, but I think it's safe to say that he's from both. I've known Amin for almost 20 years. We were grad students together at Berkeley. There seems to be a recurring theme. Didn't that happen in a couple of talks ago when Matt Welsh was here? And
more on that later.
So it's actually only Berkeley speakers were allowed this quarter. So we overlapped a little bit. We were just actually figuring out how much we overlap by. So you've actually got 3 generations here. I think I'm the oldest here, and then Amin, and then Phil from Berkeley, all in close succession. When Amin was there at Berkeley, it was the sort of rise of a project called the Network of Workstations, or NOW, which really presaged what we now think of as data centers, and that's going to be the topic of what he's going to be discussing today. At that time, he was rapidly becoming a world expert in distributed systems, and now has added to that expertise in networking and data center networks, and really became the academic authority, the authority in the academic research community on data center networks over the last few years. And he's going to be talking about some of that work today, which is why we invited him to talk about data center networks. But he's now at Google, where he's applying many of those ideas, and I'm sure, in addition, many new ones, to the way that their networks are built. So much of networking today now happens inside data centers, both in terms of from a business perspective, but just the transfer of packets and packet switching. It's just something that must be part of an introductory networking class. So delighted that Amin could be here to tell us about that.
And so actually last year, before we did this flipped classroom model with guest lectures, actually the final lecture in CS 144 last year was on data center networking, because in the past 5 years it really has emerged as this whole new area of networking, which is very different in a bunch of ways. And so the lecture that I gave last year said, hey, I'm going to take sort of the 3, what in my opinion were most important academic papers from the past few years on data center networking, or perhaps interesting, one of which was on something called data center TCP from here at Stanford, one on something called incast, a problem you see in application loads in data centers, and the last was on something called fat trees, a way of structuring your data center network. And I said, well, what's the status of fat trees? What's the status of this academic research? And I brought up the slide, which is a picture from Google New Employee Orientation. And here is Amin V, who was starting at Google in order to bring this research to Google and maybe help them improve their data centers. And so what better, rather than just showing a picture of Amin and circling him, to invite him to actually talk about that work. This is street, yeah, exactly, right. And what's actually especially, and the reason I actually had this photo, and what's I think especially funny about it, is that the person standing right next to him is a person who also came and talked here, is Matt Welsh. So at the same orientation session, there was Amin and Matt. And so it's also my pleasure to introduce and welcome Amin.
Thanks a lot, Phil. Great. So it's a real pleasure to be here. I've learned a tremendous amount from Nick and Phil over the years, and always have a lot of fun when I come here to Stanford. I think that the Network of Workstations project that Nick was alluding to is good background for data center networking. Back then, when we started the project, the goal of the project was to use idle cycles on desktop machines to do supercomputing work. Right? We thought we could build a supercomputer out of the idle cycles on everybody's desktops, right? 10% utilization, grad students aren't really doing any work. So we'll just do all the supercomputing that the world needs to do on the idle cycles. Midway through the project, we decided, so there were, in the early 90s, late 80s, early 90s, supercomputing was a big industry that was looking to take off. But it sort of, and our goal was to use these idle cycles to kill the supercomputing industry, but it sort of killed itself. So a couple of years into the project, we were going to kill supercomputers, but they'd already died. So we said, okay, well, we've got this technology, what do we do with it? Internet services, right? Now mid-90s is coming along, the internet's becoming big, so let's go after that opportunity. But sort of interestingly, at least to me, the very wise faculty members at Berkeley, there are some, even though you all are here at Stanford, forced us to learn about supercomputing network topologies. Right, so I took this class that I didn't appreciate nearly enough from Jim Demmel at the time on supercomputing and the networks that fed the supercomputers. Didn't fully get it. It was somewhere in the back of my mind. Fast forward 15 years or so, internet was really taking off. Large-scale data processing, large internet services, interactive access to thousands and thousands of computers. And I was hearing from my colleagues in industry that they were having a lot of problems with their data center networks. Really expensive and too slow. This was mid-2000s. I said, OK, well, what's the problem? What did your topology look like? I said, well, we go to Cisco and we buy a really big switch, and we put it at the root of a tree, and then we buy a couple of other big switches and put it underneath that, and then we connect servers to that. I sort of scratched my head, and I thought, OK, that's an interesting topology, right? It's a topology where we're going to connect routers together. And I harkened back to 1993 for me and the supercomputing course that I was taking as part of the Network Workstations project, and I realized that there were these other topologies that somebody taught me about at some point that did better than a single big switch at the root of a tree with a couple of others underneath it. And that's actually what led to a bunch of the work that we did on data center networking. So I guess that's just to say, remember some of the things that maybe don't seem interesting to you or arcane here in your graduate education. No telling what applicability you might have with the knowledge 15 years from now. OK, so what's different about the data center? You've learned about sort of networking, maybe internet protocols. I think networking and protocols are at an inflection point. In other words, all the books that are written about networking are about the sort of amazingly successful 40-year history of how we've gotten here to the internet. But now it's all shifting. So there aren't really any books about what it's shifting toward. But 99% of the bits that are moving back and forth on the internet are going to be moving, if not already, moving back and forth on the internet in data centers. So what's different about the data center relative to the internet at large? And so then how are things going to be different? So I just try to summarize some of the differences here about the data center. We've got a single administrative domain. Right? So the internet is all about, historically it was about multiple administrative domains, multiple autonomous systems, multiple organizations, all of whom were going to peer with one another, sort of as equals, and maybe as mistrustful equals, right? Yes, I mean, we're all working together on building the internet, but I don't necessarily trust everybody else equally. Within the data center, you have one organization, typically, that controls the whole thing. Now, it becomes interesting in a, say, cloud computing environment where I'm hosting lots of different people who don't trust each other, but the underlying servers, the underlying network, the underlying protocols that run the whole thing is spec'd by, run by, put together by a single organization. And actually, that's pretty key and pretty empowering. In other words, now we've got something that's a little bit simpler than the internet at large. Round trip times, right, between servers across the network are tiny. Right? There's no reason within a building where the round trip times can't be 10 microseconds or less. Now, maybe with buffering, they'll go up. But across the internet at large, we're talking about 10 milliseconds, 100 milliseconds, maybe with buffering and a bunch of these switches, especially with cellular devices, maybe a second. Again, when you have such short round trip times, that means that you can be much more reactive. In other words, if you have protocols that require round trips, or if you have communication that require round trips from one server to another, when you're talking about microseconds, again, that's much more empowering than hundreds of milliseconds, maybe seconds. Okay, so next, bandwidth is both more plentiful and more uniform. Right? So in the internet at large, right, capital I internet, you might be dealing with a kilobit per second link, right, somewhere. And you might be dealing with gigabit per second links or 10 gigabit per second links, all connected to the same internet. Right? So you have huge variations in bandwidth and huge variations in round trip time. Within a data center, again, I've built it. Maybe I have some heterogeneity. Maybe I've built it over time. But it's going to be much more uniform. Right? And a lot faster. Right? So 10 gigabit per second links today and having lots of them in parallel, relatively commonplace. Another key difference is buffering. the amount of buffers that I allocate to the routers and switches in the data center are much, much lower than what I might allocate to buffers and switches in the capital I internet at large. I don't know how much you followed this. Nick actually did some of the pioneering work to re-examine this conventional wisdom, but the conventional wisdom says that you buffer the bandwidth delay product within a router going through that router. And that actually, if you have 100 millisecond or more RTT, that's a huge amount of memory that you need to put into place. Still, if you apply that same conventional wisdom, in other words, if you read your textbook and say how much buffer should I have in my switch, if you got 100 microsecond RTT or 10 microsecond RTT, that bandwidth delay product becomes tiny. So the amount of buffering that I put into my switches becomes smaller. And then there's this other really neat thing that comes along with small buffers. My switches become cheaper. Right? So the amount of money I have to pay to my network vendors to buy the switches is a lot less if I need less buffering. So I have less buffering, I deploy less buffering, and this contributes back to tiny round trip times. My packets can't sit in queues because there's just not as many of them. Okay, so latency and tail latency within the data center is perhaps as important, some might say more important than bandwidth. In the internet at large, you're talking about these links that are maybe crossing the Pacific Ocean, they're crossing the Atlantic Ocean, they're really long, they cost tens of thousands of dollars, millions of dollars perhaps. It's really important to keep them full, right? I want these links to be going just at 100% utilization. If they're not, I'm burning a lot of money. People using these links are humans. Right? And so they're making requests, they're going to a website, or they're trying to buy something, and they can deal with variations in delay. Or maybe they can or they can't, but they've been trained to deal with variations in delay. So, you know, that web page took an extra 3 seconds to load. Oh well, my link is full, right? And that's good. The best way to keep a link full, again, sorry, a slight digression, is to always have a packet ready to put on that link. The best way to make sure that you always have a packet to put on that link is to have big buffers, right? So that there's always a packet that you can pull off the buffer and put on the link. Humans can deal with the latency, so just go ahead and run the bandwidth as high as possible. In the data center, we have computers talking to other computers most of the time. Yes, there's a human in the loop often, but most of the communication is from one server to another. And actually, if I want to have any hope of getting a result back to the user in time, each of these operations, they might be RPCs. They might be RPCs of the form, let me read 4 bytes from another server. That latency of that operation is critical. I can't have that operation of read 4 bytes from another server always taking 10 milliseconds or 100 milliseconds. Just can't work, because then my operation as a whole breaks down. What I mean by tail latency is that if I'm doing parallel computation that's running on thousands of servers, as we'll get to, average latency doesn't matter. Median latency doesn't matter. Imagine that I'm sending a request out to 1,000 servers, and I have to get those 4 bytes back from each of 1,000 servers. If my average and median is really fast, but my 99.9 is slow, 10x slower or 100x slower, I'm still going at the speed of that slowest request. Right? So I have to have not just low latency, but low tail latency, predictable latency. And I might be willing to sacrifice some bandwidth because my links aren't crossing the Pacific and the Atlantic, and they don't each cost $1 million. Right? The links are expensive, but they're not that expensive. And so I might be willing to run my links not at 100% utilization, such that I have a much better chance of having both low latency and low tail latency. Okay. Leading up to the mid-2000s, I would say the period sort of from the late 90s to the mid-2000s, the whole internet community, at least from my perspective, was wringing its hands because it was so difficult to introduce new things into the internet. People were coming up with brilliant new protocols, but the problem was you had to get everybody to agree to the brilliant new protocols. So how do we innovate in the internet? That was the big question that the community was asking itself. The beautiful thing about the data center is we don't have to convince everybody in the world to agree to some new protocol that we come up with. And again, this goes back to single administrative domain. Right, if I control the servers, I control the NICs, I control the switches, I can deploy new protocols and perhaps upgrade my entire infrastructure at once. So it becomes a lot easier to innovate because I have a much more homogeneous environment and I control it all. Okay, so basically introducing new things becomes much easier. Okay, so I got at this next point, moving from a client-server communication model to a sort of distributed, massively parallel computation earlier, right? In the internet at large, what we're doing is at least our mental model is, we're going to www.google.com, right? I have my laptop or my cell phone, that's a client. It's sending a request to a server, right, and it's getting a response back. That's our mental model. Within the data center, we have lots and lots of servers that are coordinating their computation and communication with one another. Again, one of these requests is resulting in lots of computation happening in parallel. Right? So the communication patterns change dramatically. And we get at things like tail latency really mattering rather than just bandwidth. Okay, and again of interest, hard to estimate, but perhaps the aggregate bisection bandwidth of the internet as a whole is about 100 terabits per second. And again, hard to know exactly what that means. So let's say, what does bisection bandwidth mean? Let's say we cut the internet in half, such that half the machines were on one side and half the machines were on the other. So what's the bandwidth across this cut? About 100 terabits per second. It's a huge amount of bandwidth. But you could put that amount of bandwidth in a single building. So, for example, Microsoft's on record with having built a 250 megawatt data center in Chicago. So what does 250 megawatts mean? That's a big number too. Rule of thumb, 1,000 watts, 1 kilowatt for a server. Very, very rough rule of thumb. So if we have 1,000 watts per server and we have 250 million watts, that means we have a single data center with 250,000 servers, potentially. And if each server has a 10 gigabit per second NIC, you can see that pretty easily 250,000 servers, each going at 10 gigabits per second, can if we were to build a network that big, and I'm not saying that anybody would be so crazy as to build a network that big, but if we were to build a network that big, you would easily beat the entire bisection bandwidth of the internet with a capital I as a whole in one building. Right? Petabits per second in one building is achievable. So this says that, again, most of the action in terms of the communication that's taking place in the internet is likely within these buildings. And there's just a massive build out, Amazon, Microsoft, Google, Facebook, ... of these data centers, these buildings going up all over the world. Okay, so this is just to say that the data center is vastly different. The scale, though, is perhaps bigger than what we think of in terms of the capital I internet. Okay, so what are we doing within these data centers? Why are they so big? Data centers are partitioned among multiple applications, and there are different ways of doing this partitioning. If I have maybe 250,000 servers in a building, maybe it's 100,000, maybe it's 10,000, there's not a single application, of course, that's running on all these machines. So I might do space partitioning. I might say, you know what, these 1,000 servers are running application A, these 200 servers are running application B, et cetera, et cetera. And of course, applications might come and go. If there's some large-scale data processing, some MapReduce, some Hadoop job, they might be coming and going, requesting 100 machines here, 500 machines there, 10,000 machines somewhere else. And of course, then there might be some scheduler that's picking among the available set of machines to run the job. There might be web services that are responding to individual user requests. And they might be provisioned to run for much longer periods of time, right? These 2,000 servers are running web search. These 500 machines are running commerce for Amazon, et cetera. So I have different models for how I might split up my infrastructure among different applications. Okay, and now there are roughly two classes of jobs that are running on the data center. They're the interactive applications and the batch processing applications. So let's consider some sample applications. Essentially, most of the interesting applications, when we think of client-server computing, are running in parallel on thousands of servers. So when I do a web search, let's say to Google, and I'm searching for terms like travel in London, it's not like I go to a single server and it looks at the entire index of the web and says, here are the 10 most relevant pages, along with some ads, that happen to satisfy the request for travel in London. All the information is distributed across, replicated across, partitioned among thousands of machines. So basically, when that request comes in, I have to distribute that request to thousands of machines. I have to go grab a bunch of information. I'm doing a distributed query, right, across thousands of machines. So I have to go grab a whole bunch of information, join them and then figure out which one's most relevant. And then create a web page. And maybe go out, find some ads that are relevant to these results. Maybe customize things, etc. Perhaps go get some news information for travel in London, put them somewhere else. Right? Thousands of different machines, maybe in parallel, right? Because I might have the search machines, the news machines, ads, etc. So I actually might fan out to multiple applications in parallel to get you that one result. So what looks like a maybe 1 or 2 kilobyte request that you make to a web service, and I don't know, 10 kilobytes, 20 kilobytes, 40 kilobyte response might involve certainly hundreds of megabytes, maybe gigabytes of data that have to be transferred among thousands of servers in real time. Right? So that response is coming back to you ideally in a few hundred milliseconds. So I'm pushing 2 kilobytes at a web server. I'm getting back 40 kilobytes. But I have to transfer maybe a gigabyte. Again, I'm making up numbers to a large extent, at least for the gigabyte number, to get the response back. Right? And in sort of few hundred millisecond budget. Okay, so that's search. Social, right? You go to, say, Facebook, and you want to get the status and latest pictures and the ads and the whatever else corresponding to all your friends. All that information isn't stored on any single machine. Right? There's no one server that has all of your friends stored on it. The social graph just doesn't partition itself in that way. So once again, everyone's updates and everyone's pictures and everyone's everything else is partitioned and replicated among thousands of machines. So when you go to, say, Facebook and you want to get facebook.com, in real time, I have to go grab information from thousands of machines, make the web page, and return it to you in a few hundred milliseconds. Okay, let's consider commerce. Going to Amazon.com, that should be easy, right? Especially if I'm just trying to look at the front page. Once again, Amazon is going to be looking at your entire shopping history, maybe the recent trends in buying from everyone else, the products that might be on sale, lots and lots of information that is spread across thousands of machines in real time to dynamically generate a front page for you that's most likely going to get you to buy something. So it's not like there's a static HTML file almost ever anymore that someone's reading from disk and putting across the network. It's, again, coordinated computation, likely among dozens of services, actually. Not all dozen services or dozens of services are going to involve thousands of servers, but probably a couple, 3, 4 are. So what looks like small requests, small responses typically requires a huge amount of orchestration across thousands of machines in the data center. So that's part one for these interactive applications. Part two is I need the highest level of availability. I mean, how often do you see Amazon.com or Google.com or Facebook.com being unavailable? It should be really, really rare. My targets typically are 99.999% availability, less than 5 minutes of downtime per year. And that's globally. Right? So in other words, here in Silicon Valley, you might see more than that. We have really good connectivity to the internet, et cetera, et cetera, et cetera. What this means is that I can't put all of Google or all of Facebook or all of Amazon or all of Microsoft in one data center in one place. I have to have lots of them. Okay? Spread across the planet. The availability is part one. Latency is part two. Right? So we actually do want to have interactive delivery of this data to the users, modular, what I was talking about earlier. And so what that means is not only do I need lots of data centers, I need to spread them across the planet, right? Because of the speed of light latency going to tens, perhaps hundreds of milliseconds, depending on where you're accessing the service from. This says that I need to have multiple copies of my data. Right? So it's not just enough to have one copy of the web or one copy of all of the friends on Facebook or one copy of shopping history for Amazon. I need multiple. So this drives both the number of data centers and their placements globally. Okay, so that's the interactive side. Batch processing side, to build the index for the web, to basically keep track of what's happening in social, to figure out Amazon's shopping history, I have to basically process petabytes of data, right, that might amount to, say, all the information on the web in some cases. I'm constantly processing them for multiple applications to build summaries, indexes, right? And this is the batch side. So I have huge amount of computation here, But I also have a huge amount of computation on the batch processing side, running things like MapReduce or Hadoop, going over petabytes, moving to perhaps exabytes of data. And this isn't a real-time thing. This isn't happening in milliseconds. This might be happening over hours, perhaps even days, but it's happening constantly. And the number of servers that I need to go over petabytes of data, right? So again, if we just do rough math and one server has maybe a few terabytes of data, and you need to go over petabytes of data, pretty soon you can see that the batch processing over lots of data is going to require thousands and thousands of servers. So this is what's driving. And in essence, we have lots of data centers, lots of servers in them, but none of them are big enough. And we don't have nearly enough servers or nearly enough computation in them. OK, so that's how data centers are different. This is the sort of jobs that we're running. What do current data center topologies look like? And this goes back to what data center topologies might look like if you were to go with the textbook topology. We deploy servers in racks. Right, so we're going to put some number of servers in a rack. Might be 40-ish, might be 80. I'll have a switch at the top of the rack. So it's a so-called top-of-rack switch that is going to interconnect all these servers together. Right, so I might have 40 ports, let's say. I'm going to take the servers, plug them into this top-of-rack switch. There'll be some number of ports going up from the top-of-rack switch to what might be an end-of-row switch. Right? So I have rack, 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 all in a row. At the end of the row, I have an end-of-row switch, and fiber coming from these racks over to this end-of-row switch. And this might get me to however many racks I might have in a row. Let's say that number is 20 or 30. That starts getting me into the thousands, perhaps, of servers. So now I have lots of these rows. Each row has an end-of-row switch, and there might be a core level of switching. And there'll be uplinks, right, coming out of the end-of-row switches, connecting into the core. Conventional wisdom says there's no way that I can build a network such that all of these servers can talk to each other at full speed. Now, what does this mean, again, from looking at it from a bisection bandwidth perspective? If I were to cut my data center in half, right, just put a line down here, and let's say that all the servers on this side wanted to talk to all the servers on this side, and then all the servers on this side wanted to talk to all the servers on this side. Everybody has to go up to the core. Right? There's no locality in the communication. Everybody has to go up to the core and then back down. So how much bandwidth am I building in here is the question. The more bandwidth I want to build in here, the more it's going to cost me. Right? The more ports I need from routers, the more optics I have to put in, the more fiber I have to lay, et cetera. So that's the question that a data center designer has to ask and answer, is how much bandwidth to provision here, and to a lesser extent, how much bandwidth to provision here. The connectivity from the server to the top-of-rack switch is usually pretty straightforward. Right? If I've got a gigabit NIC, that's what I've decided I want, 1 gigabit per second. Well, I'm probably going to have a top-of-rack switch with gigabit ports. If I've decided I want to splurge for 10 gigabit per second NICs, then I'm going to have a top-of-rack switch with 10 gigabit per second connectivity. And typically, these things here are single chips that are non-blocking. Right? What that means is that there's a switch, right, and whatever packets you put in can go out at full speed. The point here is, though, that if I have some bandwidth going down this way, I might have less going up this way. Right? So that's called an oversubscription point. So imagine that I have 40 servers each with gigabit connectivity here. It might be 40 gigabits per second of bandwidth. What if I only have 4 links, each a gigabit per second going out? That means I'm oversubscribed 10 to 1. So that how I've provisioned my bisection, if you will, over here, is that I only have 1/10 of the maximum bandwidth. Or maybe I've decided that I want to oversubscribe 100 to 1 or 200 to 1. Right? Again, it's just a question of how much I want to pay. And it's a question of what my applications need. Right? And then applications need just not in terms of bandwidth, but in terms of latency. I don't want to necessarily run my links at full speed, because if I run my links at full speed, I might have to buffer. I might have these sort of tails of latency that start to be painful. So typical guidelines are, depending on whether you're doing gigabit or 10 gigabit, and depending on how intensive your application is, that you would oversubscribe maybe 2.5 to 1 to 200 to 1. And still, this staged deployment here, multiple stages of switching, gets pretty expensive. So this becomes a substantial pain point for the operators of the data centers, and it becomes a substantial pain point for the applications, right? I'm running on 1,000 servers, 2,000 servers, and literally for every request that comes in for travel in London, I'm sending out a request to 1,000 servers, and I'm collecting responses from 1,000 servers. If I'm oversubscribing things substantially, things might come back slowly, packets might get dropped, etc. Okay. Yeah. Depends on the various numbers. So certainly the way that I've drawn it here, where there are 2 links up and only 2 servers connected to these top of racks, yes, it would be adequately provisioned. But you might imagine that there might be 40 servers here or 20 servers, etc. Sure. Yeah, just think of this as a pictorial representation. Again, you have knobs to turn with respect to how much oversubscription you want to introduce. And the more oversubscription you introduce, again, the more potential congestion you have, but the cheaper your network becomes. Okay, so in trying to build your data center network, you have a number of goals. One that I've argued for is that it should be possible to provide full bisection bandwidth between all pairs of hosts. And I'll provide some numbers for that momentarily. But it should at least be possible such that the aggregate bandwidth of your data center as a whole would allow all hosts to talk to each other at full speed. Next, economies of scale. So the price per port should be constant with the number of hosts. And this maybe seems obvious, and we've grown accustomed to it becoming obvious. What I mean here is that if I want a 10,000 server data center, the amount I pay per network port should be the same as whether I want a 1,000 server data center or a 100,000 server data center. And the way to go at this is that if I want some amount of computation, let's say I want 1,000 servers worth of computation, I'm used to thinking, hey, if I need 2,000 servers worth of computation, I pay twice as much. Similarly for storage, right? If I want a petabyte of storage, it should cost X. And if I want 2 petabytes of storage, it should cost 2X. Right? I have this model of being able to just go buy servers from Dell or HP or whoever, plug them in, and put in as many as I want, and I get that much computation. Same with disks. Right? However many 1 terabyte, 2 terabyte, 3 terabyte drives I need, I go buy those. If I run out of space, I go buy more of those. Turns out that for networking, doing this is hard. Right? In other words, if I go buy this 4,000 port data center network, the 8,000 port version might cost way more than the 4,000 port version, much more than 2X. We'll see why. This third point, anything, anywhere. What I mean by this is that you should be able to put any computation you want on any server. But the way that data centers are built, especially if you look at the last picture with sort of different oversubscription points, I have to co-locate my computations to basically points in the tree with good locality. So if I go back to this picture over here, what I'd really like to do if I have some communication-intensive application is place them all underneath the same top-of-rack switch, because I got lots of bandwidth there. And if I can't do that, I'd like to keep them all under the same end-of-row switch. Right? I want to keep them as low, right, in this topology as possible. But if you just think of this from a bin packing perspective, if I restrict my choices in where I can place computation, I'm going to wind up with lower levels of utilization. And in a world where I'm virtualizing my network, right, lots of virtual machines that can potentially run anywhere, right? Think of Amazon's EC2. I can put my Amazon EC2 Linux VM anywhere, but now I have a bunch of them that want to communicate with each other. Okay, now I can't put them anywhere. I have to put them close to one another. And that means I have to find some top-rack switch that happens to have enough servers available, enough cores available, whatever the answer winds up being, to support that placement. So now the network, interestingly, determines what level of utilization I get out of my compute. If I have lots of bandwidth available between arbitrary points in my network, I can perhaps drive my utilization up higher. Okay. Right. And so what this says is that we really want scale-out networking. And what I mean here is that we've come to expect scale-out computing and storage. Going back to the Network of Workstations project that Nick was referring to, we were trying to kill supercomputers. In the early 90s, late 80s, the model with computing and storage was scale-up. You bought the biggest computer you could afford, or that was necessary for a particular job, and once that computer didn't have enough compute capacity for your job, you threw it out and you bought a bigger one. Right? And then when that one ran out of compute power, you threw out and you bought a bigger one, right? The next model up from your vendor. What's changed over the past 20 years is you don't think that way anymore. When you run out of compute, you go buy more servers. You don't throw out the old ones. When you run out of storage, you don't throw out your storage appliance and buy a bigger one. You buy another storage appliance, right? And you've got another petabyte, right? And so we take this as completely obvious, and we should. That's how it should be. Networking doesn't work that way, right? If you want to take your, again, 20,000 port data center network and expand it to 30,000 ports, the literal state of the art is you throw it out and you buy a new one. There's not a notion of, hey, just go buy 10,000 more ports or 5,000 more ports. You throw it out and you buy a new one, right? So networking is still stuck in the world that compute and storage was stuck in 20 years ago, right? Where you have to scale it up rather than scale it out. And we're starting to transition. But we still actually, I would say, as an industry, and certainly from an academic perspective, haven't figured out how to do scale-out networking, where I can just go buy. So my view would be, you want more ports, you go buy more ports. It's a 1U. You plug it into a rack, and now you have more ports for your network. Right? You need 30 more ports, go buy another 1U. You need more bandwidth, you need another terabit for your network, go buy that bandwidth module, plug it into your rack, and now you have another terabit per section of bisection bandwidth. That's not how networking works. Right. Okay. Okay. So I think I've made all these points. Okay, and so let's zoom into an individual server that's running in the data center and what that might look like. Again, sort of from a cartoon level. CPU, perhaps one or more CPUs. Each CPU has multiple cores. Right? So in this picture, I have 4 cores, each with their own cache, and then a shared L3 cache. Okay, I have memory within my server in the form of DRAM, maybe tens of gigabytes of memory being common. And I access the memory over my memory bus. Might be at the high end today, DDR3 1600. And this has multiple lanes of 100 gigabits per second to the memory with about 5 nanoseconds of latency. Right? So when your high-end server, if you want to go from, if you want to go off cache, right? You don't fit in the 10 megabytes, 20 megabytes or so of cache that you have over here. You go over your memory bus at about 100 gigabits per second per bank with 5 nanoseconds latency. You have your local drives, a few terabytes of storage. You have your NICs, maybe 10 gigabits per second, again at the high end. And you access that over your PCI bus. High end, it's 3.0, 16 lanes. And that delivers about 128 gigabits per second over the PCI bus with about 250 nanoseconds of latency. Okay, so there are networks over here too, right? And this is all within the box. So this is your commodity chip, right? This is your commodity DRAM, commodity disk, commodity NIC. And now I have increasingly commodity chips from multiple switch vendors. On a single chip, at the high end, I might get 24 ports of 40 gigabits per second. Interestingly, just as we've gone with sort of chip multi-core, networking, at least today, is going in multiples of 10 gigabits per second. So this 24-port 40 gig switch is just as easily a 96-port 10 gig switch. Everything's in multiples of 10 gigabits per second. So if I want to build 40 gigabits per second, I just take 4 10 gigabit per second lanes. If I want 100 gigabit per second Ethernet, I take 10 of them. So the math doesn't quite work out, but this could almost be a 10-port 10 gigabit per second switch. It could be a 24-port 40 gigabit per second switch, or it could be a 96-port 10 gigabit per second switch. And the fastest ones have roughly 150 nanoseconds of latency through them. So I think the interesting thing that, and this might be, again, this is a single chip. This might be your top of rack. So the interesting thing is that the bandwidths here and the latencies here are not ridiculously different from the bandwidths and latencies that you see over here. So now you're potentially getting to a world where your chip multi-core processing, accessing DRAM and storage, if it has to go off the local cache, you might be able to use these, perhaps in series, to get at the memory and storage, right, of remote machines with comparable latency and comparable bandwidth. So now we can really look at a world where we're building our computation across hundreds, perhaps thousands of servers, treating remote disk, I didn't draw a remote flash, and remote memory almost as if they were local, right, from a networking perspective. Okay, so let's see why that might be interesting from a perspective of parallel computation. So I'll go to Amdahl's slightly lesser known law. Amdahl's law typically refers to how basically the sequential portion of a parallel computation dominates the runtime, increasingly dominates the runtime of a parallel computation. Amdahl's one of the pioneers in supercomputing. In the late 60s, he came up with a rule of thumb, more a rule of thumb than a law, for how to provision a parallel compute engine, a supercomputer. Right, how much compute, how much storage, how much memory should I put in my parallel computer? And his rule of thumb was for every megahertz of processing power, I should allocate a megabyte of memory and a megabit per second of I/O. Late 60s, 67, 68, 69. So if you fast forward, and this, again, it's a rule of thumb, depends on the computation that you're running. Fast forward to 2012, it wouldn't be unheard of to have 8 cores in a machine, each going at 2.5 gigahertz. Understanding that it's not that simple and you can't multiply, but I will multiply. This might work out to 30 to 60 gigahertz of computing power within a single machine. And certainly, I might put 24 to 64 gigabytes of DRAM within a single machine today. So the balance here has been maintained according to this rule of thumb. But again, the standard is that I have today a gigabit per second of bandwidth, and I might over-provision it by 5 to 1, 10 to 1, or more, maybe 100 to 1 in building my data centers. So roughly, while this balance is maintained, I'm perhaps under-provisioning my network by a factor of 60 just at the NIC level, and maybe a factor of 600 or 1,000 or more if I account for the fact that I have oversub going up the topology in a large-scale data center network. What I want to try to get at here is that we're trying to build efficient data centers. These data centers might have 100,000, 200,000 servers in them. They consume a huge amount of energy. They cost a tremendous amount of money. But if I'm building computation that is starved on I/O, that means that my servers are sitting around idle, waiting to do work, right? I send a request, and if I'm sending that request across a very thin pipe, much thinner than what the CPU and memory can potentially feed, I'm underutilizing my DRAM and I'm underutilizing my compute because I'm under-provisioning my network. And so that's the problem that people are facing in the data center environment right now, where they might be under-provisioning the I/O in their network by just ridiculous amounts, factor of 100, factor of 1,000. The point here being that if you invest more in your network, you might get a huge ROI, not just in terms of your network, but in terms of your compute and in terms of your DRAM, in terms of your storage, because you get much better utilization out of them. So I might argue that you should have just huge amounts of bandwidth to every server. Not 1 gigabit per second over provision, but perhaps 40 gigabits per second. And if you push that out to 100,000 servers, because you want to be able to run any computation anywhere, right, in your large-scale data center, this says that maybe you need to build something that has a bisection bandwidth of 4 petabits per second. Right? And that would be what you would need today. Right? This isn't the grand challenge, but what you would need today to actually run balanced computation, going back to Amdahl's law, right, if it's held, today across all these servers. And remember, the internet, capital I as a whole, has about 100 terabits per second of bisection bandwidth. So we're saying, OK, we want to put a factor of 40 more bandwidth in a building than the whole internet. OK, so these are rules of thumb. Does it really matter? When I'm doing my batch processing, when I'm running my Hadoop, when I'm querying for travel in London, when the fundamental operation that I have to do is sort, actually, underneath it all. Right? That's the fundamental operation across, say, a database join operation. I have to sort huge amounts of data. So the database community has a yearly competition. How fast can you sort a huge amount of data as a predictor for how fast these higher level operations might go? So currently, the huge amount of data, in quotes, is defined to be 100 terabytes. Right? So basically, can you build a system, and you can build it however you want, it can be as big as you want, but take 100 terabytes of data on disk, spread across multiple machines, read it in, sort it, and write it out. Okay? So basically, there's going to be a bunch of records, keys and values, sort all the keys. They're originally in some semi-random order. Read them off disk, sort them, write them out. Okay. So in 2009, the winner of the yearly sort competition was Yahoo. They sorted 100 terabytes of data in just under 3 hours. And the aggregate rate, if you just do the simple math, is they went at 10 gigabytes per second. And they ran on 3,452 servers to sort this 100 terabytes of data. But then the interesting thing is, at least for me, the interesting thing was that they went at about 3 megabytes per second per server. So that's 20-ish megabits per second. So now remember, we're talking about servers that can drive, a single modern server can drive 10 gigabits per second with 1 core. And I might have 20 cores, et cetera. So I have 3,000 servers going at 20 megabits per second, when one of these servers should be able to go at 10 gigabits per second. Okay. So the question that we asked at UCSD is, OK, we can't get 3,452 servers at a university, but we can get 30. Okay. And so can we beat this number by a factor of 100? And if we can beat this number by a factor of 100, we can set the world record in sorting. And how cool would that be, right, to do that in a university? This whole separate talk that I'd really enjoy giving, but I'll skip. So we built the system. It turned out to be much harder than we expected. But in fact, we went factor of 100 faster. And what this says is, 2.5 gigabits per second per server. Right? If you do the bytes to bits translation. So what this says is that you actually, so you can sort the same amount of data on, we wound up doing it on 52 servers. It didn't go quite as fast as we hoped. You can do just the same amount of work on dramatically fewer servers. So the same system we built to set the world record for sorting actually turned out to be the world's most energy efficient sorting system too. There's a separate category for energy efficiency. And what I've learned, I've done some work in energy efficiency in the past. Typically, the best way to be energy efficient is to go as fast as possible. Just get the job done and move on. So efficiency means not just, OK, go really fast, but efficiency means burn as little energy as possible. This is just trying to connect the dots back to the previous set of slides. You really do want to build balanced systems. You really do want to enable the servers to communicate with one another at substantially more than the oversubscription rates that we have in data centers today. So this 20 megabit per second number, what I'll note is that their network was provisioned at 200 megabits per second. So they still had even inefficiency on top of their 200 megabit per second number. They had a gigabit per second link coming out of their servers. They oversubscribed it 5 to 1. Right, so they were still under-delivering even their network by a factor 10. But the question we wanted to ask is, hey, should you build a balanced system such that you actually can go at maybe 10 gigabits per second and really drive the system to its capabilities? Skip this. OK, so now coming to how would you build a data center network that can drive the system at full speed? Right? Can I have everybody talking to everybody else at full speed? And how can you do it so that it's relatively cheap? So that I'm not spending just a huge amount on the switching infrastructure relative to the servers. OK, and so I want to give you just a little bit of intuition on how. So what I showed you earlier is how data center networks might be built today in terms of top of rack, end of row, and core. Here's a similar but slightly different way to do it. And this is the fat tree thing that Phil was referring to earlier. So the goal here for this work is to use identical commodity switches to interconnect lots of servers together. So I'm going to use a simple example with what you'll see here is 16 servers interconnected with one another. But what I want to illustrate is how I would get these 16 servers to be able to talk to each other at full speed using just 4-port switches as my building block. Okay, so let's say that you can go and buy a 4-port switch really cheap. It's the commodity box that happens to be the best sort of price-performance ratio. Right? And it's the same kind of thinking that you might have, right? If you're going to go buy a server from Dell, you sort of try to figure out, OK, I don't want the fastest, greatest, most wonderful thing that's out there because I'm paying too much for it. Right? Pick that commodity point where it's that sweet spot in terms of, for that extra dollar, I still get a little, enough additional performance. OK, now think that at this point in time, this 4-port switch is the sweet spot. But of course, I want to build a network that's much bigger than 4 ports. So how do I organize things? OK, so let's start with what we call pods. Take 4 of these 4-port switches and organize them in this manner. So each pod is a 2-array 2-tree. Right? Means basically what I have is 2 levels and 2 links up. If you look at this highlighted portion, what you can hopefully convince yourself of is that for arbitrary communication patterns among these 4 switches, however these 4 switches want to talk to one another, I can schedule that communication across these 4 links such that all switches can talk to each other at full speed. Okay? So if I have a good scheduler, if 1 wants to talk to 3 and 2 wants to talk to 4 and 4 wants to talk to 1, whatever permutation you come up with, as long as it's bijective, meaning 1 to 1, I can do the scheduling here such that everybody can talk to everybody else at full speed. OK, so now this gets me to 4. Now how do I get to 16? Basically add another level to the topology. So now I take my 4 pods, right, and I scale out now what you can see horizontally. I add another level. I take my same switches, 4 ports, and introduce this core layer that interconnects the pods together. And once again, what you can see is that there are 16 links here for the 16 servers. There's 16 links here, and there's 16 links here. So again, for arbitrary communication patterns, bijective among these 16 servers, everybody can talk to everybody else at full speed if I can schedule these links appropriately. So now I've gotten to 16. Well, I might need more. Maybe I want to go to 64 at another stage in the topology. Okay. And I can make this arbitrarily deep. Yeah?
Wouldn't a machine in pod 0 be able to talk to another machine in pod 0 faster than it could talk to a machine in pod 1?
In terms of bandwidth, if you can schedule it appropriately, it should be identical. In terms of latency, certainly latency will vary. Yeah, you're absolutely right there. So if I have 150 nanoseconds here, I have to pay 150, 150, 150. So you're basically going to have to then provision your system for that worst case latency. However, I'm going to argue that the latency through the switches, if I keep the number of hops moderate, say 7 or 9. Maybe that adds a microsecond, but I'm nowhere close to having that microsecond be my main bottleneck yet. I hope 5 years from now, you ask that same question, and I say, drat, right? That microsecond is killing me. That microsecond isn't yet killing me. I have lots of other inefficiencies in the system. But in terms of latency, you're absolutely right that it will be different. In terms of bandwidth, it should be the same. OK, so this is called a rearrangeably non-blocking topology. Okay, so that means that for, again, arbitrary communication patterns, I can map things to deliver full bandwidth among all the participants. So for this 3-stage topology, the math works out as follows. I can use 5k squared over 4 k-port switches. Right, so if I have 4 port switches, 5k squared over 4 works out to be 20, to support rearrangeably non-blocking communication over k cubed over 4 hosts. Okay, and that works out to be 16. So if I went to a 4-stage topology, this number would go to k to the 4th over 8. Okay, so that this cubic or et cetera becomes quite powerful. Now, it turns out the commodity switches typically are much bigger than 4 ports, which is really nice. So commodity switches are typically, say, 24 or 32, 48 ports. And so if I had a 48-port switch, I can get to 27,648 switches in a 3-stage topology using 2,880 switches. Right, so I can have the illusion of a 27,000-port switch with 2,880 individual switches organized in this 3-stage manner. And now the other nice thing is that I don't care what these link speeds are. They can be 1 gigabit, 10 gigabit, 40 gigabits, 100 gigabits, as long as I organize things identically and hierarchically in this manner. I get full bandwidth among all the servers. Now, it could still be the case that I just don't need full bandwidth. Right? For my application, I just don't communicate that much. I don't want to do that sort quite as fast. You can still oversubscribe, just as you did before. Right? But the point here is that you're using exactly the same commodity element, organized with basically all the same stuff organized in this multi-stage manner. So these switches wind up being extensions of the commodity compute and storage elements at the bottom. Yeah.
So it seems like an appropriate question, but you guys, like 2 years ago, switched to OpenFlow to managing all this infrastructure. Are you doing fancy things in order to manage how the traffic's provisioned using software-defined networking? Like is that providing a lot of this improvement, or is it, even with like dumber switches, is this topology still a huge gain?
So with dumber switches, this topology is a huge gain.
Okay.
Yeah. So basically, the main win here is that I'm using commodity switching elements.
Okay.
Right? And so I'm not going and buying specialized, expensive 100-port, 200-port high-end switches and putting them one big one, the biggest one that I can afford, at the root of a tree. That's the key point here. So I was going to, and I'll now only spend a little bit of time talking about software-defined networking and what Google's doing. So let me go ahead and skip a bunch. Yeah, more questions? Go ahead.
Yeah. So if you know a priori what the communication is going to be like,
yeah,
then it works. But what if you have some random communication?
Okay, so let's talk about how I would do the scheduling. Yeah. So the way I have a couple of choices. One is I can have an omniscient scheduler that is going to sit off to the side and figure out how to rearrangeably allocate bandwidth to these links. It turns out, actually, people aren't sure. Depending on the definition of the problem, it's NP hard. No matter what, it's really hard. NP hard or really hard, one or the other. So the way that it's typically done is I do flow hashing. Okay, so I'm going to take my packet. I'm going to look at the source IP. I'm going to look at the destination IP. I'm going to look at the source port. And I'm going to look at the destination port. And I'm going to put it into a big hash function. And I'm going to say, for packets that belong to this flow, I'm going to mod that by, in this case, 2 or 16 or 32. And I'm going to map that to this link. Now, this is going to make a bunch of assumptions. It's going to make assumptions about the size of the flows, mostly, and the evenness of the flows among the destination servers, which is built in. But it turns out that if you have a bunch of mostly uniform flows, this works brilliantly. Just static flow hashing at each stage is going to distribute the packets beautifully. Now, the other thing that you could do is Valiant load balancing. Leslie Valiant from Harvard many years ago said that, hey, if I just spray the packets among my links, I'm going to get perfect load balancing. Okay? Problem is TCP. TCP doesn't like reordering. So I actually don't think that's inherent. That's probably a whole other discussion that we could have. But if I spray packets rather than flows, I then don't have to make any assumptions about flow size distributions. But then the packets over here, because they're following different paths, may arrive out of order. And then TCP gets confused, thinks that our congestion windows need to go down, et cetera, et cetera. So bottom line, you can't have an omniscient scheduler. The problem's too hard. Flow hashing works pretty well. Not perfectly, actually. And so the flow hashing causes substantial pain. So your question is actually a very good one. And hey, maybe there's an opportunity to build congestion control protocols, layer 4 protocols that aren't as sensitive to reordering as TCP is. Okay. Good. Okay, let me talk for just a second about another question. Yeah.
In your slide with like the formulas for like for K port switch, you have these things.
Yeah.
I noticed that the number of total ports in the system divided by the number of usable ports in the system is 5.
Is 5.
Which seems like a reasonably high number.
It's a pretty high number.
What is a more, like to compare, like I don't, off the top of my head I don't know, what would that be in like a more traditional model?
So it again depends on the bandwidth that you're delivering. You're going to be using a lot of switches here.
Yes.
But the point I want to make is that if you go buy a really big switch from Cisco or Juniper, there's actually a lot of switches inside that box. It's not like they have this one ginormous ASIC that delivers 500 ports of 10 gigabits per second. They're actually putting maybe even the same ASICs on. Anyway, so that's again a whole other discussion. Number of chips will be the same. There's no magic here. It's just a question of going after the commodity. Okay, so let's talk about software-defined networking since the question came up. Let's talk about a little bit about what Google does in its WAN. So we talked about the data center now. We are at this inflection point. I'll only spend a couple of minutes on this, but historically, the whole goal of network protocols has been to eliminate centralization. Right? The internet has been about, hey, as long as you can attach to any member of the internet, you're part of the internet. And one, you don't trust everybody. Two, you can't maintain centralized state about the internet. So we're going to run fully decentralized protocols. We're going to have philosophies around soft state such that basically you come up, you learn what you need to learn from your directly connected neighbors, and that's going to be enough to get the job done. So every network element acts autonomously, uses local information, and tries to approximate global targets for connectivity, etc. But it turns out that actually building fully decentralized protocols can be, and usually is, much harder than using centralization. So it's this paradox from my perspective. The internet could only have been this successful if we adopted full decentralization. But if the internet is going to scale to the next level and perhaps to deliver the necessary levels of performance and security and availability, it has to adopt centralization. And let me just make a very rough, hand-wavy computer science argument about it. If I have n routers and they want to learn global system state, you have to exchange n squared messages. And the amount of time it takes to learn global system state is log n steps if people are pairwise exchanging information with their directly connected neighbors. So that's roughly inherent. Right? I have to exchange n squared messages among n routing elements, and it'll take log n steps for everybody to learn global system state. Now imagine that I have a central controller that all the routers can connect to. I have to send two n messages, right? Everybody sends one message to the central controller, and then everybody gets information back. And it takes 2 steps for everybody to learn global system state. So I'm going to argue that it's inherently more efficient, actually, to build a central controller than a fully distributed one. Now, the fully distributed one has advantages, but if I'm in a single autonomous system administrative domain and I control everything, and maybe I can take my central controller and replicate it using all the knowledge that we've gained about replication and fault tolerance and high availability since the internet first started. Remember, Paxos didn't exist, for those of you who know what Paxos is, in late 60s, early 70s, etc. Can I take that knowledge from distributed systems and apply it to networks and make it inherently more efficient? And so that is what software-defined networking is about. Does class end at 5:20? 5:30. Okay. So let me see what's the best thing to cover. What SDN is doing, what software-defined networking is doing, is taking essentially most of the brains of individual switches and routers and pulling them out. So how we did things in the past is we took switches and routers and they ran the protocols. They exchanged information with their neighbors. They learned whatever state they needed to learn about, say, global connectivity. And everything that they needed to know, the truth about the network, was contained within each network element. What we're doing with software-defined networking and work on OpenFlow is basically taking that intelligence out and putting it into some central element. So now I might have a routing service. Maybe I have virtual machine manager. And these things centrally are telling an OpenFlow controller how to program basically low-level hardware on individual switching elements to do forwarding of packets. Right, so what does a switch do, right? I mean, it's going to take a packet, it's going to look at its header, and it's going to say which output port to forward the data on. Figuring out how to program these hardware tables, typically the software ran on each of these elements. And again, they talk these fully decentralized protocols among themselves to do so. What we're saying with SDN is we're going to pull that out. I'm going to have this routing service. This routing service might know the full topology of the network. Right? When I'm a data center so if I'm the internet, capital I internet, I have no idea what the topology of the internet is. I can't control it. I don't know what it is. No one knows what it is. So I have to take my best guess and learn information from my peers, etc. If I'm building this 250 megawatt building, I plan what my network looks like. I know exactly what the topology is. I place the POs, right? I put the racks where they're going to go. I figured out how many fibers are going to go from each top of rack switch, etc. There's some database, right, that the routing service might talk to. It says this is exactly what the topology looks like. Now, of course, switches might be down, links might be failed, so I have to account for that. But I roughly know what everything looks like. So I can potentially just go tell all of these switches, hey, here's what your forwarding tables look like. Because you are a stage 2 switch, and your 4th port is connected to this host. And your 5th port is pointing up to this other switch. Because that's, and if it's not, something's broken. Right? Somebody may have miswired it, or maybe a host is down, etc. And this is, again, a fundamental shift from how internet protocols have happened to date. Yeah?
Is there some kind of fallback in that situation where if a link goes down and you lose communication with the central controller, that you fall back to that decentralized model so that you can learn enough state to maintain operation?
Great question. And that's one we have to answer. And so again, we don't know, right? And different people are doing different things. It turns out doing that is complicated. So you have to weigh the pros and cons. One thing you can say is, okay, I lose my link to the central controller. A couple of options. One is I don't have a special link to the central controller. The central controller is talking to me in line over my existing network, and I have lots. The thing about this topologies you saw earlier, there's lots of multipath. So, okay, but that's hard too, by the way, and that is a whole nother can of worms. Other thing is, okay, I've lost my link. But now what I've done is I've exposed myself to additional failures. In other words, all the information that I have is still probably fine. Right? It's just now if something else fails somewhere else, I'm not going to be able to be programmed. So can I build my control plane, right, my connectivity to that central controller, with sufficient availability where that shouldn't matter? And again, you can answer that question. I think the answer is yes. That since the control plane is low bandwidth, right, it's not going at terabits per second, you can probably build it with sufficient levels of availability by two-way or three-way redundancy to make the chance of that happening pretty low. And when it does happen, it's not that the network melts down. It's just that I'm now vulnerable to additional failures. Or you could have the hybrid, right, where you run the fully decentralized protocols and, as a backup. OK. So Google has applied SDN to the WAN. And the main reason it's applied it to the WAN is because, so I talked about 100 terabits per second of bisection bandwidth in the WAN. This graph is dated. Google today has about 10% of that. So 10% of the whole internet, 10 terabits per second of that WAN bandwidth goes through Google. This graph shows over time through about 2010 the percentage of WAN traffic that goes through Google. So WAN traffic is growing tremendously. Google's share of WAN traffic is growing faster. Yeah.
Is stuff within Google's, like Google using its own WAN between its data centers?
It's a great question. Of the number I just quoted to you, a lot of it is YouTube. However, in addition to this
not
is
100%, clearly. Right?
Not 100%,
So, yeah.
but a lot of it. You can imagine that video is dominant. But Google, as I'll get to in just a second, runs its own private WAN. Right, so there are actually two networks. One is AS15169, which is Google's autonomous system that connects to the rest of the internet, and that's what this is measuring. There's a second network that connects Google's data centers together. And we're not sending much video between those. That network is bigger than this one, right? So, and we have to run both. Right? This is the public, yeah. The Atlas doesn't have an ability yet to measure our private one. So let's see, what's, again, in the 3 minutes. For our private WAN, we're building an SDN. And the reason is that the cost of running a WAN is really, really high. Right? And since our portion of it is growing faster than the internet at large, we have to have a way of making it economical. So if you go to most ISPs, Comcast, Deutsche Telekom, et cetera, they'll say that they're really worried because they can't make money on delivering bits. Right? So why? Why is it so expensive? Hardware. High-end routers, transport gear. Transport gear is actually something that I've only learned about over the past few years. Right? Routers don't connect to other routers. Routers connect to transport gear that have big lasers that send the bits over thousands of kilometers. These are as expensive as these. Okay. And so this is a big source of cost. And then, of course, there's laying the fiber across the Pacific or the Atlantic or across the country, across the continent, et cetera. So this all costs a lot of money. Over-provisioning the network costs a lot of money. If I'm going to deliver super high levels of availability, I'm going to have to be prepared for failures. And so that means that I over-provision the number of links that I have. Because I do shortest path routing, typically, a bunch of bandwidth goes unused because I'm following the shortest path. Human cost of running the network grows super linearly with the size of the network because humans have to think about the interaction of all network elements with all other network elements, which is quadratic. Right, so that, again, I could say a lot more about that, but it just becomes a lot harder to run a network as you add more bandwidth to it, especially across the WAN. So right, this is our private WAN. This connects roughly 14 data centers spread across the planet. And what we wound up doing, because at the time that we started this effort, there was no SDN open flow switches. We wound up building our own switches. The idea here is to split up the hardware that we needed from the software that was going to run it. Right? So we built our own switches with a thin layer of software that was controlled from a central agent. Right? So this hardware could be what the hardware is. And you can imagine that we try to make it inexpensive. And then with the protocols that we ran on it were the protocols that we wanted to run on it. And as far as what ran on the box, it's something that basically takes commands from a central controller and says, set my forwarding table entries to look like this. Right? And that says, when I want to get a packet on this port, and it has this header, forward it out this other port. I am oversimplifying, but it's not that much different. And again, in my 0 minutes left, what I will say is that the one application that we deployed on this SDN was traffic engineering. And what traffic engineering means is that we can basically use non-shortest path forwarding to send data across our network. We can figure out how to tunnel traffic from one place to another depending on the criticality of the traffic. So what we do in our network is we drive our most important links at about 100% utilization. So this is basically showing over time across one of our WAN links the percentage utilization. Typical state of the art in the industry is to run links at 30 to 40% utilization because we want to be protected against failures. But because we can actually do traffic engineering on a per traffic class basis, we know that if we happen to lose some of the links corresponding to this trunk, there's actually multiple 10 gigabit per second links behind this graph, we can reroute a bunch of the traffic along alternate paths, and we can make sure that the highest priority traffic keeps getting through, while some of the lower priority traffic might wind up getting throttled or dropped. Okay, so I'll stop here. Yeah.
Links, and then you have
This was a graph of a single trunk, big trunk across the WAN, and it's showing all the different traffic classes.
right, but
aggregated
you're saying
together.
that it's running at like 97% utilization, but that's okay because you've got alternate paths that you can shove stuff into.
Yes.
So that means that your alternate paths are probably running out of load.
No, the alternate paths are also running at very high levels of utilization because there's a mix of high priority and low priority traffic on all the paths.
Right.
And we can make sure that there is a mix of high priority and low priority traffic on all the paths. Now, it is true that under failure, some of that low priority traffic is going to get throttled. And, and we can live with that. Yeah.
Were you saying that the control signals are out of band, or do they go through the same network?
That's an open design question for software-defined networking. And each has big pros and cons.
Why don't we, since we're just over time there, why don't we thank Amin for giving us this talk, and then if you're interested,